Okay, so this video is going to be talking about statistics. Statistics is a science, even though it's usually taught by math teachers. It's the study of using numbers to support science. So that's why I'm doing a fast and dirty introduction to statistics, which I'll say wrong at least 8 more times in this video. This is statistics from the point of view of a field oceanographer, so keep that in mind in case it doesn't jive with the stuff you've learned in class. There are 2 types of stats we're going to go over, descriptive and inferential. Descriptive you probably already know, even starting in middle school, is mean, median, mode, and that stuff. Inferential, though, is the new stuff, t-test, ANOVA, things of that nature. And we're going to use inferential both in your candy data sets, but also in the larger data sets we're going out and collecting right now. So these words are not interchangeable, and make sure you understand them because I'm going to be asking you where are your descriptive statistics, where are your inferential. So it's important to know. Just to refresh about descriptive statistics, I put in this picture of distributions. So when we did the taste test for Coke and Pepsi, we made histograms of distribution for each class. Remember, that would be the ability to, we would put on here what, like, percentage right or wrong, and then here was how many people did that. So you sort of got like this column graph like this, and that was normal distribution. In normal distribution, the average, the median, and the mode all occur basically pretty much in the same spot. And then it's important to know normal distribution or not in order to do different statistical tests. It also tells you a little bit about your population. The 2 different skews, one of the ways you can tell something is skewed without making a histogram is where median and mode are in relation to mean. If median and mode are to the right of mean, it's a left skew. If median and mode are to the left of mean, smaller numbers, that means it is a right skew. I'm assuming you already know how to do mean, median, and mode. I will show you next class how to do that in Excel. Please, for the love of God, I once saw a student sitting with their Excel open and a calculator in hand, calculating things and then typing them in Excel. Save yourselves the heartache. Don't do that. Then there's also measures of variability. So all of these things describe the data set. What's the average, what's the mean, what's the median. But variability tells you how wide it is. That's range is probably the simplest one. It's from here to here. Standard deviation tells you how far off mean you are. Standard error takes into account sample size and is, of course, Ms. Baskin's favorite. But it's really important to understand that these do not test your hypothesis. If you have a mean for one group that's this and a mean for another group that's this, that actually doesn't mean they're different. You have to do inferential statistics to do that. So please, in your results sections, don't tell me group 1 had this mean and group 2 had that mean, so they're different. They may be, they may not be. We just don't know yet because descriptive statistics can't tell us. Yes, I'm recording this one at school. Okay, inferential statistics, on the other hand, doesn't tell you much of anything except whether or not you have different groups. They test your hypothesis. Remember, everybody's null hypothesis is always there is no difference. So if you reject your null hypothesis, the groups are different. So you're always trying to reject your null. You guys frequently want to make statements like, this data proves my primary hypothesis. You guys do very good science here at Mast, but nobody ever proves their primary hypothesis. You can support it, which is what you hope to do, but at best you're rejecting your null hypothesis, which means you either have to pick your primary or alternate. The verbiage matters here, so I want you guys to practice thinking about it in that way. In terms of inferential statistics, we're going to do a couple of tests. These are the 4 most common that we do. T-test. I will spend some time teaching you t-test in class. We never calculate it by hand, but I'll show you how to do it in Excel. Please don't look up ANOVA. If you look up the ANOVA test, you're going to quit science because you think it's terrible. But nobody ever calculates ANOVA by hand. It's always done in a computer. I will show you how to do that. Correlation you've probably actually done before. If you've ever made a scatter plot, you did correlation. And we've done that, and you would show line of best fit. And there is actually after you make the line of best fit, there's a test that goes along with correlation called Pearson's that will give you a number and tell you if they actually are different. Chi-square was like flipping the coin. If you flip a coin, you should get your expected values are half of heads and half of tails. Chi-squares does the same thing. Did you get what you expected to get? It and t-test are a little confusing on which to do to tell if 2 groups are different, expected and observed, but we'll do more of that as we go on. So I need to talk to you about p-value. So inferential statistics, all of them spit out this thing called the p-value. And I hate this picture because it should be written as lowercase. P-value is always lowercase. P-value. And I even did it wrong here too. I want to remind you, and those of you in stats probably know this, when you have normal distribution, and I think you saw this when we made the histograms, most of your values are going to fall within a certain area. So the most common would be your mean, then the next, and the next, and the next. If you were to actually measure the area under the curve, there's some calculus for you, 95% of them fall within basically here to here, which means only 5% of in normal distribution of your values fall in these little edges. P-value is what allows you to reject your null hypothesis. If group 1 and group 2 are compared to each other and you get a P that is, and the magic thing is less than 0.05, what that tells you is that 95% of the values of each group are different. So I don't know if you recognize this, but 95% different means that less than 5% are the same, which is the same as less than 0.05. Do you guys remember that percent and decimals work like this? What your p-value is saying is that 5% of your values that you got in your data overlap amongst your groups. If that's the case, in science, we say they're statistically different. What that would look like in a distribution is maybe you have two groups. There's one and there's another one, and theoretically only this little bit of observation would overlap. That's what we're looking for. That's why p-value, the magic number, is always 0.05 or less. By the way, that's for field studies and most science. In medical studies, they actually, when we're talking about people, we want error so little that the p-value has to be 0.001, less than 0.1%. The same. Okay, so let's look at that another way. So here it is. If you guys are in statistics, you've probably seen the confidence interval, which is where 95% of the values fall, is the confidence interval. And then in this little area, if you fall outside that 95%, it is statistically an outlier. So if we were talking about comparing, I don't know, let's say this is group A. We have group B over here. As long as the only place that they have overlapping values is in the little outlier bit, they are statistically significantly different. Please keep in mind, kiddos, that significant has meaning now. You can't use the word significant anywhere except where you've done inferential statistics. This should say type 2. Type 1 and type 2 are types of error. So type 1 error is a false positive. It's where you should be, where the null hypothesis, no difference, is what actually is happening, and you fail to reject it. You're like, oh no, there's really a difference when there's not. Type 2 error is the opposite. You say there is no difference when there really is one. I just put this picture in here because I've always hated this picture. It's actually out of my stat book from when I was in college. But this is important when you go on to the next level of science. Certain statistical tests accept different types of either alpha or beta, type 1 or type 2 errors. And we're going to talk about them more as we learn about different statistical tests and which one you choose. So now what? Now what? We got to make graphs. So why do we make graphs in the first place? A graph has a specific need. It's not to quote unquote show data. If you just want someone to look at your actual raw data, you use a table. That's what tables are for. They look at the data more deeply. Graphing is to show relationships between different groups, or to show whether or not your hypothesis was supported, or and whether or not you were able to reject your null. They should never show the exact same information. So like you may have a table that's all your raw data, but your graphs are only your means. That's how you know which goes where. So most of your projects for Candy will only be graphs, but I suspect the things from the profiling and other larger projects, we will have actual tables. All right, I made you this terrible graph. So the idea behind this was that somebody went out and asked people their favorite flavor of ice cream. And some 80 people said chocolate was the best, 60-something said strawberry was the best, and they're just wrong. And then a lot of people like vanilla. By the way, the correct answer is, of course, chocolate. This is a terrible graph. First of all, there's nothing labeled on the y-axis. I'm assuming that's number of people who claim that was whatever. But the real issue is, when you make a line graph for this type of data, it suggests that if you were to go out and ask people, is your favorite flavor of ice cream a mixture of strawberry vanilla? That some 70 people would say that. Likewise, is your favorite flavor of ice cream strawberry vanilla? They would say that. But we don't have anything that actually suggests that. This is what we call discrete or category-based data. I know you guys do qualitative and quantitative already, so this is along those lines. This graph should be a bar graph / column graph. That would more accurately represent it. And keep in mind, when we did our histograms, histograms and bar graphs are not the same. When we did histograms, our bars touched. They touched because that implies that there's, data in here. We leave space in between on a bar graph or column graph or whatever you want to call it to show that we don't have any information for in between here. That's a real basic of graphing, so make sure you do that one well. See, they didn't leave any space. This is a bad graph. This is another terrible graph. I hate this graph. There's a couple things going on here. Again, axes just aren't labeled at all. There's no space between the bars, which is also not good. But let's talk about color for a second. I suspect this graph had something to do with boys and girls based on the archaic color choices. But 10 to 20% of the people in the U.S. have some level of color deficiency. And the most common version of that would make it very hard to tell the difference between this level of red or pink and blue. They're the same intensity. So one of the things that we frequently do is you need to pick colors that differentiate well for people who have color issues. You also can use patterns. So if you need colors that are similar in tone or intensity, you can put lines on them. That's an option in Excel. Just keep in mind that you want to use the same color for the same. Don't use this for, let's say, girls and this for boys, and then in the next one use green and yellow. You want to guide the reader by picking color choices and pattern choices that carry throughout and make sense. So keep that in mind. This is another terrible graph. This one's really bad. There's so much going on here. First of all, let's talk about font size. This is much too small. Your minimum font size on a table graph, whatever, should be, on chart graph, should be 14. This is like tiny. That's like an 8. See, this one's nice and large. This one tiny, tiny. So keep your font sizes legible. You guys are young and have much better vision than people my age, so bigger is better. Again, don't make a chart 3D. Like this, I don't know if you can tell, this goes back. And people struggle with 3D charts because they don't know, and can I zoom in? I can. Okay. So like, should you measure to the front of the bar or the back of the bar? That's one of the problems with making a 3D chart. You don't know where the line actually goes. I think on this one, it's the back. I don't know. It's vaguely terrible. Don't make a 3D chart unless it's absolutely necessary. And that would be like if you're actually comparing 3 variables and you have a z-axis, don't do that. I know that you guys use pie chart in economics. Economics is the one exception to this rule. If you are, ding dong, if you are doing anything in economics, feel free to use a pie chart. Any other science, don't use pie charts. We would always use a column graph or a bar graph. Also, these people are big fat liars trying to manipulate you. Look, the scale on the Y, it doesn't start at 0. It starts at 5,000. That's because if you carried these lines down all the way down the way they're supposed to be, the difference from here to here, not that big a deal. They're trying to make it look like a bigger deal than it is. That's way sketchy. Don't do that. This is the last slide. I pinky swear. So column graphs, the types. Column graph is the most common, particularly when we do our candy. It's for categories instead of like continuous variables, so things that are quote unquote discrete. And so, by the way, I use the word column graph and bar graph interchangeably, which I should not. If you go into Excel, they make like this is what they call a bar graph, which is fine. If I tell you I want a bar graph, I don't ever want the sideways one. I like the vertical one. Bar graph. Thank you. Bar graph, column graph, all the same thing for this purpose of this class. So when you guys do colors and stuff in candies, we're going to be using mostly column graphs. Same thing with when we do fish, like the numbers of each species of fish, column graph. That's so we don't suggest there's like, if we got 10 of a mummy chog and 20 killifish, we don't want to have it continuous so it looks like we would have 15 of some hybrid of them. Linear graphs we use sometimes when we do measured weights and variables. So if you were looking at time or whatnot, you could use a linear graph. Some of you are going to be using line graphs when you look at things like, I don't know, your profiles on the beach, because distance would always be linear. And then finally, the scatter plot. We've done scatter plots in this class already, where we measure this and then find the line of best fit. If some of the measurements you took for the candy data may end up being that. All right, so I'm going to stop here, guys. I know this is kind of a longer video. Hold on to these notes, and we will be working on actually doing some of this stuff in Excel next class.